And now we'll cover the natural response of RL circuit that contains a resistor and an inductor, as you can see in here. So I will use this particular circuit to explain this concept, and in this particular circuit we'll assume that this switch is actually closed for a very long time, and by closed for a very long time means that the inductor can be simply replaced by some sort of a simple wire, and because we replaced it with a wire, that technically tells me that this resistor is shorted and this resistor is shorted. Remember, it's like the switch is at this particular point in here, and for that I will have an initial current flowing through this, which is just simply I of S, because if you think about it, if the voltage here is 0 and the voltage here is 0, that means there's no current in either of the resistors. That means the current source is just simply flowing through the I of S. That's basically it, and the inductor is now storing some energy. And then at some sort of a time, and we're going to call it time 0 in here, what we will do is we'll open this particular switch. By opening the switch, we'll isolate this part in here, okay? And what we'll end up with is the following. We'll end up with just a simple inductor connected to a resistor in a single loop circuit. Okay, so this one here is the inductor, this one is the resistor. And of course, because the inductor initially has the following, it has an I of S, actually it's going upwards, it has an IS, okay? So because it has some sort of an energy, so it naturally gives that energy to the R, which consumes it, and eventually the L will lose all the energy that it stores, and that's why we call it natural response. We can also call it zero input response or source-free response, because I don't have any sources for this part of the circuit after time t0. So what I'm interested in is the following. I want to find pretty much the current, for example, the actual current I of t, the equation for the current in here, and I can also find, well, that's what I'm interested in because it's the same current through the inductor and the resistor. And of course we can say, well, let me just write these equations. So we can say, well, we have V R of t is just the same as V L of t because they have the same exact voltage. And we know also that the voltage across the inductor, this one here, V of t. So what I'm saying is the voltage in here and the voltage in here are the same. So, and they're both equal V, by the way. So I'm just going to basically put this one here plus minus and V. Okay, and V of R and V of L, we know them. Well, simply V of R is just simply I times R. Okay, and let me just double check. This I is actually hitting the R in the positive direction. Okay, so that should be positive here in terms of passive sign convention. And on the other side, we know that V of L is just simply L times the derivative of I of t divided by d of t. And if you think about it in here, this current is actually hitting the negative port first for the inductor. Okay, because now I'm focusing on the inductor, so the current is going that way. So it's hitting the negative first. So what I need to do is I need to put the negative in here. All right, so that's what we have now. So I'll do a little bit of algebra, and what I'll end up with is the following: di of t divided by d of t. And I believe that will be plus, I think it's 1 divided by L divided by R. Just write it clearly here. It's actually L divided by R, I of t equals just simply 0. Remember, it's like this is I of t in here as well. And this is of the form that is dx of t divided by d of t plus 1 divided by tau x of t equals some sort of a constant. In this particular case is 0. So it's a first order differential equation, and again it's first order because if you take a look at the circuit, all we have is one energy storage element. We don't have two, so one energy storage element connected to a resistor, so it's a first order circuit. And this is the differential equation that describes this particular circuit, and it's of this general form. So now I'll go ahead and just solve this particular differential equations just to see it. And by comparison, by the way, you will see that tau is just simply L divided by R, and its unit is usually in seconds. But anyway, let's solve this equation. What I'm after is figuring out what the I is. Okay, so let's do that. So what we have is di of t divided by d of t equals negative 1 divided by L divided by R, I of t. Okay, which is di of t divided by I of t is just simply negative 1 divided by L divided by R, and that here is multiplied by t. We take the integral of both sides, so that will tell me I'm going to go from I of t0 all the way to I of t, and that will be d of y divided by y equals negative 1 divided by L divided by R, and the integral from t0 to t of d of x, for example. And then what we have in here is just simply the logarithm of I of t divided by it naught equals negative 1 divided by L divided by R, and that's here is t minus t0. And for the sake of simplicity, we'll assume that t0 is just simply 0. and the IT0, we know, well, we can either call it I0, and we know in our cases, if you think about it in here, this is I of S, and this is I of T. So initially, the voltage or the current through it is just simply I of S, which is coming from this particular source in here. All right, and just remember the current across an inductor cannot change, because this is the equation for current for the voltage across the inductor. If we allow the current to change instantaneously, that means we're allowing this particular derivative to actually go to infinity, which makes the voltage across it infinity, which makes the power infinity, and it's not allowed. So an inductor opposes the change in current. Okay, so going back in here, I'll substitute these values that we saw in red. So that will tell us, well, it's logarithm of I of t, and I'll keep it in I of 0, -1 divided by L divided by R, and that will be t. We take the exponent for both sides, and that will give me I of t divided by I0 equals e to the -1 divided by L divided by R of t. Okay, and that means IT is simply I0, or IS if you want, -1 divided by, technically this is tau, or L divided by R of t, and that here is the solution for that differential equation, which tells me this is it, and this is for t is greater than or equal to 0. And remember again, the I of t across an inductor right before switching and right after switching is the same, so that's why we say t is greater than or equal to 0. All right, so now let's assume that what we're interested in is also the voltage across the inductor in here. So let me just copy this here so that you see it. Okay, we'll copy this, okay, and just put it in here. So let's assume that we're also interested in the voltage across the inductor or the resistor, basically the V. Well, I'm going to deal with it as if it's the voltage across the inductor. So V of L of t is just simply, we know, based on passive sign convention, it has to be -L d of I of t divided by d of t. So that's simply, it's -L times I0, and the derivative, it's just simply -1 divided by L divided by R. I believe e to the -1 divided by L divided by R of t. Of course, this here goes with this particular one. So let me just do that. Okay, and that will become basically negative times negative. Remember, it's like, because this is also I0, and this one here, and this one here, I think, and this one here. That's how it becomes. So negative times negative is the same, so it becomes I0 R e to the -L divided by R of t. Okay, and that's VL of t, and that's exactly for t is greater than 0, not greater than or equal to, because if you think about it, the VL of t at 0 minus, basically right before switching, remember that right before switching this was a wire, so the voltage here was just simply 0 before the switch. Okay, and after the switch you will see that VL of 0 plus, basically right after switching you substituted 0 for this t, and you'll end up with the following, which is just simply I0 times R, which sort of makes sense because what we have is we have I0 basically, or I of S, is flowing through the R times R, and that's basically the voltage across it. Okay, and of course you can continue by computing, for example, like let's assume that I wanted to compute the power, I can do that. So let me do that for you. So for example, let's assume that I wanted the P of L of t is just simply IL of t times VL of t. Okay, so we multiply these two in here, so what we will have is I0 e to the -1 divided by L divided by R t, and the whole thing we multiply it by I0 R e to the -1 divided by L divided by R of t. Okay, and that's simply I0 squared times R e to the -2 L divided by R of t, and that's basically for t is exactly greater than 0. Again, because before 0, basically there's no voltage across it, so the power across it was 0, so it's exactly after 0. So in summary, what we have is we have an RL circuit that basically has a single inductor and a single resistor, and the inductor contains some sort of an initial storage and initial energy stored in it, and of course that initial energy stored will appear as if it's an initial current in it. We called it IS, or maybe I also can call it I0, just basically as initial, okay, current. And the way we can compute the current after switching, basically right after the zero switch, what happens, like we'll end up with this particular equation. This is of the form that we've seen before, which is just simply C1 plus C2 e to the negative t divided by tau. And just remember, in this particular case, tau is just simply L divided by R. Okay, so, and of course this is in second, okay, so that the unit here has to be unitless. Okay, so in this particular case, C1 happened to be 0 because it's a natural response. I don't have any sources external, and C2 happened to be this particular one here, and that's basically negative 1 divided by tau. And this is for the t is greater than or equal to 0 for an inductor, because the current before and right after 0 is the same. So at 0 it's the same because it doesn't change. And if we wanted the v of t, simply we take basically L times the derivative of this equation, and that's what we end up with. Okay, and this is for t is greater than 0, because before 0 the voltage across the inductor was 0, and right after 0 it becomes non-zero. It actually jumps from 0 to something that is other than 0, which is I0R. And the same goes with the power. The power before it was 0, and then afterwards it starts basically to give off the power. That's what we will see. And of course this power in here has to be, actually it has to be negative. So if you actually go in here, because I multiplied I times V, but if you think about it in here, this I and this V have a negative in here, so I have to have a negative in here. The reason why I'm emphasizing that negative is because I know that the inductor in this particular case, it's actually giving off power. This is a positive entity, this is a positive entity, this is a positive entity, so that means I have to have a negative in here.